All right, so today we're going to talk about linear and angular quantities and how they are related. So just a reminder what we learned about kind of our rotational quantities. Let's say I'm using a reference here, some starting position, and this is some rotating rigid object. So when I talk about a rotating rigid object, you'll hear this sometimes, rotating rigid object. Basically what you're assuming when it says rotating rigid object, that every point along the object moves together. So all points move together. And when I say move together, I say move at the same angular speed. So they have the same angular velocity, no matter where on the object it is. So I could pick a point here, and let's say that this reference line rotates to this position right here. This point is going to move through some position at some omega. If I look at a point here on the rim, it's going to move through that same position. It's going to take the same amount of time for both. And what you're going to end up with is that omega 1 is equal to omega 2. And that could be true for all points on this rotating rigid object. They would also have, if their speed changed while they were there, they would have the same angular acceleration as well. So all points along that rotating rigid object would have the same angular acceleration. Now the problem is that while they have these same angular quantities, their linear velocities are completely different, because while they travel through the same delta theta, so they have the same angular speed, they do not travel through the same linear distance. So we define that linear distance as the arc length. We use the lowercase s. I think that's what you do in pre-cal as well. And its standard unit would be meters, although you'll often see this in centimeters and things, but the SI unit is meters. So the arc length would be the arc path traveled. So there would be an arc length here for this one, and there would be an arc length for that one. And so when we look at what our linear velocity is, our linear velocity during that time would be the change in, would actually be distance over time. Probably just easier to do distance over time. So our distance over time, when we put that kind of in our variables here, would be our arc length over the change in time. So the change in arc length. And what they can do sometimes is they'll do this as like change in s. And like this would be s equals 0, and then you would have any other change. So like if I went from this position to this position, this could be s1 and this could be s2 based on this arc length versus that arc length relative to some reference. So you have to just kind of be careful with some of the definitions. But I just prefer just to do like arc length over time. And so these are going to have different values. So because S2 is larger than S1, V2 is going to be greater than V1. So the linear velocity for this point here is going to be smaller than the linear velocity here. Well, where are those linear velocities? Well, what happens is if you were to rotate an object, we have this thing spinning here. It's moving in a horizontal circle, so you can kind of see that bobber. Now, what happens if I let it go? Well, if you were to pause your video and watch it in slow motion, you probably would have seen it actually move approximately in a straight line. And so that's kind of what happens, is objects, according to Newton's laws, want to move in straight lines. So objects have a tendency to move in a straight line unless there is some sort of force pulling them towards the center. Well, we haven't talked about the forces that allow objects to move in circles yet. That's coming. But since the string is what was keeping it moving in a circle, when I removed it, the object wanted to go back to its moving in a straight line, because it was always trying to move in a straight line. It was just being prevented from doing so. So what happens is that at any point, kind of along that circle, objects are always wanting to move in a straight line. So this point here on the rim is wanting to move in a straight line with some velocity v2. Well, that velocity would be based on the arc length that travels in that time. Well, this one travels a bigger arc length, so it has to have a bigger linear speed than this point here, v1. So while these 2 points have the same angular speed, the linear speed v1 is less than v2. And actually, if you were to kind of draw out kind of a line of speeds, at the dead center, that center point doesn't have any linear displacement. It always stays in the center. And then the next point out would have a little bigger speed, and the next point out would have a little bigger speed, until you have even bigger speeds kind of throughout, until you get to the edge, where the point on the edge would have the maximum value for that speed. So the points on the edge will always have the largest velocity. Well, why is that? And what do we know about this velocity? So that's kind of what we're going to talk about here. Well, one thing is that this velocity is a tangential velocity, and I usually use a v subscript with lowercase t to represent a tangential velocity. You can just represent it with a linear v. You can just do that. But I like to do the VT to remind myself that it is always tangent to the circle. So the linear velocities are always tangent to the circle. So no matter what point I pick, if I were to draw the velocity of some point, that velocity of that point must be tangent to the circle. The tangential velocity would be still measured in meters per second, because it is a linear quantity, and it is the instantaneous speed in that particular direction at that particular point. So it is always tangent to the circle, and it is an instantaneous value. You could have an average tangential speed. You can have an average tangential velocity, but we're talking here about the instantaneous value at that point along the circle. Just a reminder that a tangent line is a line that only touches the circle at one point. So that's what these are here. So you have to kind of be careful. The tangent is also always perpendicular to the radius. You often have to draw these velocities. So sometimes it helps to draw the radius first. So if I draw this particular radius, I want to pick this point here on the circle, then I need to make sure that that is a 90 degrees, so for my tangential velocity there. Now our definition of tangential velocity is going to match this definition up here. Our tangential velocity is by definition the change in arc length over the change in time. And once again, that is going back to a definition where we are assuming that we have some sort of initial s equals 0. I have some position 1 and some position 2. And if I were to take my arc length for position 1, that would be S1. If I were to take my arc length for position 2, that would be S2. So my delta S here would be S2 minus S1. Or if you set S1 to be this point and you set this one S1 is equal to 0, then it's just equal to S2. So it doesn't really matter which way you do, but technically that's the definition we're looking at here. So this is our mathematical definition of tangential speed. It's a velocity when you add a direction. It's difficult to do linear directions unless you're at kind of the main horizontal vertical coordinate points. So often we deal in magnitude here for that. Now, I want to relate this tangential speed to my angular speed. So I want to do that. I want to figure out how they are related. So omega is change in theta over change in time, and we know that our tangential speed is delta s over delta t. And I want to know how they're related. Well, starting with this definition of Vt is equal to delta s over delta t, how would delta s relate to a rotational quantity? Well, we know that from pre-cal, you might have seen something that s is equal to r times delta theta, or sometimes they just do s is equal to r theta. Or you can do delta s is equal to r times delta theta. There's different ways that it's written. But if I use this definition right here, which is kind of the more general physics definition of arc length, r is your radius. Delta theta is, of course, your angular displacement. And delta s is our arc length. Throughout some motion, the change in the arc length through that. So if I take this and I rearrange, and sorry, not rearrange, but sub this in, right up here, I get that my tangential velocity is going to be r delta theta over delta t. Well, I'm going to use a property of kind of multiplication and division here, and that I can rearrange this. And so I can say that Vt is equal to r times delta theta over delta t. Well, what do you know? Delta theta over delta t is omega. So that means my tangential velocity is r times omega. And that is how we relate our linear quantity of tangential velocity to our rotational quantity of angular velocity. So this gives us our Vt. I'm actually going to call it a tangential speed, so I don't have to worry about direction. And that will be measured in meters per second. R is our radius. It would be measured in meters for the SI units. And omega is our angular speed. We're going to use your speed here. In radians per second. So if you notice the units here, you get meters times radians per second, and that just gives you meters per second. And that's just a reminder that a radian is actually a placeholder. The definition of radians actually comes from this definition here, where the definition of delta theta is the arc length over the radius. So this is units of meters divided by meters. Delta theta is technically dimensionless, but we give it units of radians, so we have a placeholder. So we also know that we haven't just forgotten to write degrees. So you have to kind of be careful with that. So anytime you multiply radians by any other units, the radians just disappears, okay? Because it's technically just a placeholder. And then the direction of Vt would be determined for the vector quantities would be determined just by kind of looking at the picture. So just like we have a tangential velocity, if say I was accelerating and I had an angular acceleration, then that means that these points are going to have an even bigger speed. So let's say I was speeding up around the circle, or I could be slowing down. It could be a negative acceleration. But let's say my acceleration is in the same direction as I'm rotating, so I'm speeding up. I'm going to have some sort of change in velocity. So for this point right here, you know, at this point that I'm at, I could have some omega 1, and I could have some omega 2, but I could have a corresponding tangential velocity up there, and I could have a tangential velocity there, and base it some radius from the center of the circle. So the I would have some sort of change in linear speed and change in rotational speed. So I know that in rotational terms, my angular acceleration is change in omega over change in time. In linear terms, my tangential acceleration would be my change in tangential velocity over the change in time. So this is one definition of tangential acceleration. So it is the change in my tangential speed. It would have units of meters per second squared, just like a regular acceleration. It is a linear acceleration. It's not the only linear acceleration, that we have to be careful. Our speed is only in this direction, but we actually have different definitions of acceleration here, which we're going to have to be careful of. But our definition of tangential acceleration is the change in tangential velocity over the change in time. So if we go through kind of the same process, I can substitute in, I erased that my VT is also equal to R times omega. If I want to relate my linear quantities to rotational quantities, I can sub in this VT is R omega in here. So I would get AT is the change in R times omega over the change in time. Now, my assumption is that my radius stays constant because this is a rotating rigid object, which essentially means that that radius is constant and can be pulled out, because if I were to do this, this would be like R omega 2 minus R omega 1, and that R would factor out. So that would just be R times omega 2 minus omega 1, which would just be R times the change in omega. So I can always kind of pull that R out. So we get AT is R times the change in omega over the change in time. Once again, I can rearrange that. R is change in omega over the change in time. And then this is our definition of alpha. So I get AT is equal to R times alpha. And I have this new relationship here. So basically my tangential acceleration is also equal to R times my angular quantity. And that is the general trend. I have a linear quantity, and it's going to equal radius times my angular quantity in general. So I get VT is R omega, I get AT is R alpha, I get delta S is R delta theta. And what do you know? None of those equations are on your AP Physics 1 formula sheet. Ooh, that's really rough, because these are really important. You will use these all the time because these are going to be the link between our linear and rotational quantities. For example, if I have a pulley and I have a string attached to that pulley, and I have a linear acceleration of my block as it falls, and it's causing my pulley to rotate, there is a link between this acceleration, this linear acceleration, the angular acceleration, and it is this equation, but they don't give that for you. So you have to kind of be careful with your definitions and so forth. But that gives you a way to link the two together. So there you go, linear versus angular quantities.